Hello, everyone, and thank you for attending. My name is Roop Ganguly. I'm a Chief Solution Architect at Bigstream Solutions. I'm going to be talking today about hardware-based acceleration for Apache Spark. And before we get started, I just want to outline the objectives of the session. They're really twofold. One is to just bring hardware acceleration to everyone's attention and let folks know that it's here and it's usable, definitely tryable for your Spark applications. And the second is, as you get deeper into it, it's important what architecture of acceleration that you choose, because there's hardware implications that bubble all the way up to your Spark application. And so that's what we're talking about today. So let's start with why we're here in the first place. And in one word, it's performance. I'm not going to belabor the point. Data engineers, data scientists, I'm raising my hand. I'm a former data scientist about 5 years ago. But basically, we all want performance. We want to use bigger data sets, longer look back in our analytics, more sets of data. And this need is ever growing. That's what we're seeing both in our marketing research with our customers. And sort of concurrently, so to speak, the issue is that CPU-based approaches to meeting these performance demands are not quite hitting the mark. There's a number of reasons for this, and we'll talk about those. I think one of the primary ones is that Moore's Law has actually been slowing down for over 5 years now. So CPUs are not getting faster as fast as they used to. And so consequently, what we're seeing out there in the user base is customers are missing their SLAs, having tough times meeting their deadlines, getting cut off from data sources that they want to use. And so, this is an important issue, maybe one of the primary issues in terms of moving forward with Spark Analytics. So that said, let's start with what the approach is today. And as we all know, what we all run our Spark applications on is CPU clusters. That's the most prevalent way that Spark is run. And Spark does a fantastic job of distributing computations, distributing data, as we all know. And so it's become very, very popular. There's a huge adaptation rate. And what happens when we want to get more performance? Well, the most common way we address that is with cluster scale up or cluster scale out. So scale up refers to making the individual nodes in the CPU cluster more powerful, adding more cores, adding more memory. Scale out refers to adding more number of servers to our clusters. And they can obviously be used in conjunction. But what we're seeing, and there's two primary drawbacks to this. One is it's costly. These servers are not cheap. They're actually getting more scarce these days, is what I'm seeing in the literature. And so it's, and even on the cloud, in the managed environment, Azure and AWS are charging, premium prices for larger nodes and larger clusters in a lot of cases. The other problem that we see is that it's typically sublinear in terms of performance improvement, meaning that if you get n times more the hardware or n times more the servers, you don't get even close to n times the performance. There's a number of technical reasons for that, including I/O scaling, network scaling, L2 cache contention. I won't get into all those details. So we've come up with other solutions in today's environment. One category is I call code optimization, basically writing better Spark code, right? Putting your filters before your joins, avoiding redundant table scans. Included in that, I've loosely included caching approaches. So there's ways that if you draw your data from certain locations, certain URIs, the system will automatically cache that data for further use for locality. And then the other, probably most familiar one is Spark configure optimizations, right? So the number of executors, number of cores per executors, executor memory, driver memory, all those things can be played with to optimize the performance of your application. Another sort of CPU-based approach I'd like to talk about briefly is software-based acceleration. So what is that? That's basically under the hood implemented Spark tasks via native code. And this runs on CPU instances, so there's no need for additional hardware. Bigstream has developed software-based acceleration. It's seamless, it's zero Spark user code change. But all of these approaches really complement the scaling of CPU clusters. I don't want to make it seem like acceleration is a replacement for CPU clustering. In fact, it's complementary to CPU clustering. So, software-based acceleration is a way to accelerate without the advanced hardware we're talking about today. And just wanted to show a very quick result. This is a set of business intelligence queries called TPCDS that we ran on standard Spark 3.0, and then with the software-based acceleration provided by Bigstream. Just a quick plug is that it's available today on Marketplace. If you search for Bigstream, you'll find it there. So what we're looking at here is the speedup numbers. How much faster does this acceleration make your Spark code run? You can see the parameters of these runs. This is a 4-node cluster with CSV data, standard CSV data. And you see we can get some pretty impressive performance improvement just with software alone. So even without the specialized hardware we'll be talking about today, acceleration is a viable way to get performance. But our subject today is to take performance sort of to the next level. And that's where hardware acceleration comes in. Hardware acceleration, in a nutshell, involves running our analytics on what I'm calling programmable or specialized hardware. So field programmable gate arrays, FPGAs, graphics processing units, GPUs, application-specific integrated circuits is another approach, ASICs. And all these hardware choices are designed for efficient execution of specialized code, meaning that the hardware adapts to the actual application. So contrast that with a general purpose CPU, which is programmable, but doesn't necessarily morph to adapt to your specific application, right? So these are all interesting hardware approaches. ASICs typically support domain-specific workloads, hence the name. I'm not going to be talking much more about ASICs, but they are in use for analytics and particularly AI today. But the two leading technologies I'll be talking about is FPGAs and GPUs. Now they provide another level of flexibility of programmable hardware, right? And they provide the efficiency that we're talking about, the efficient execution. The issue is, and why isn't everybody using this type of hardware for Spark right now? The issue is that they don't natively connect to any big data platforms, right? Some middleware is needed to make that connection. The way Spark, you download it from the Apache site, it runs on your CPU cluster, right? That's not true necessarily of these hardware platforms. But if we can bridge that gap, both of these approaches can provide performance and a significant power and cost advantages, and actually, again, complement CPU scale up and scale out to make it more cost effective, more power effective. So that's the goal. The other thing I'd like to bring out today is that the hardware acceleration market is trending. So, this is happening. People are using this. And some evidence that I want to present is some interesting research done by ARK Invest. This is a recent article that they wrote. And if you look at going from, in the next decade, what they're saying is that the accelerator market in terms of hardware is going to grow by many factors. And in fact, on top of that, it's going to actually exceed the expenditure over that of CPUs. That's their prediction. And as you can see in the last bullet there, this is driven by us. This is driven by big data, analytics, AI, data scientists, et cetera. But I want to make clear that this research, it deals with the hardware expenditure, right? It's tracking the hardware expenditure in terms of the market. Nothing is sort of said here about the software that makes this stuff usable, and that's really what I'm going to be talking about today. But the point of this graph is that the accelerator market is taking off, and it's a trend we need to watch and take advantage of. So I'm going to give a high-level architectural comparison of these two technologies, GPU and FPGA. Again, this is at 1,000-foot level. I'm not a hardware engineer. Again, I'm a data scientist. But I think that's the correct level to take a look at it and start thinking about acceleration for our analytics. So looking at the top picture of the GPU, basically what you can think about is that it's just a number of capable compute lanes populated by basically CPUs that are more specialized. So they have a reduced set, but they're very, very efficient. They have a reduced set of operations that they support. And you just have a very high number of them packed onto this hardware platform, right? So the benefit of that is that you can get a very high degree of data level parallelism. If you have data that you can compartmentalize into these different lanes, then you can get a ton of parallelism and a ton of performance out of that architecture. The other interesting thing is that similar to CPUs, they're programmable via an instruction set. And so it's a more familiar programming model in that sense than some other hardware accelerator platforms. The challenges with GPUs is that they use a SIMD, which is single instruction stream, multiple data set approach to computation. So each of these compute lanes is computing the exact same instruction set. And so the branch divergence, meaning ifs, conditional jumps, things like that, can be very costly and can cause inefficiencies. And we'll get into that a little bit in the next slide. The other thing is that we've done some experimentation and reading some of the literature. Power consumption can be kind of high for this highly parallel platform for some types of analytics operations. Okay. In the lower picture, you see FPGAs, and FPGAs are basically configurable at the logic gate level. So I'm talking your OR gates, NAND gates, XOR. Basically, that's how you program an FPGA. So in that sense, there is no instruction set architecture for an FPGA. It's really at the logic level. And so that flexibility gives it certain advantages, which is basically that the logic can be configured per operation and really maximize the efficiency. They can be very, very well tailored to the operations that you're doing. And that also results in lower power consumption per computation. The other thing is that this issue with branches and irregular parallelism, heterogeneous parallelism can be leveraged on the FPGA. And another advantage that they tend to have is that there's very high on-chip bandwidth between compute elements that are defined. But again, this really higher degree of flexibility comes at a cost, is that you really have to understand FPGA architecture and think about your application in terms of logic gates to take advantage of this. So that's kind of the interesting piece with the FPGA. So I mentioned about irregular computations, and this is just an example where the two architectures behave differently. And what I want to do is, show how the architecture affects the application, right? That's all this example is for. So if you look at the application code in blue, it's a piece of analytic written in, let's say, Scala for my Spark application. It's a retail application. And it says if the shirt size is equal to large, then do the code in green. Otherwise, do the code in red, right? And that's represented by the green and red arrows for the computation in the legend. So in the GPU case, because of the SIMD, single instruction stream architecture that GPUs inherently have, we have to split up the branches of the if statement into two separate execution streams that have to be executed at two separate times, right? Only one instruction stream can be executing at the GPU at any given time. And so you see that the entire computation is split up into sort of two epochs. Whereas on the FPGA side, because we can configure the compute lanes to do what's called MIMD, multiple instructions stream, multiple data, we can do them simultaneously if we have enough compute lanes. And that's another issue where the parallelism in the two cases varies. But all I want to illustrate here is that there's architectural differences that bubble all the way up to the application level. And so that can affect your performance. And these are the kind of things. So we don't need to learn how to program this hardware, right, as data scientists. What we need to do is understand the architecture and how it bubbles up into our application. What is our application doing? Which applications are going to run better on which architecture, acceleration architecture? So that's really what I'm trying to point out with this example. So just a high-level set of hypotheses, observations from someone with 5 years experience in the field. I've used this technology. I've done a lot of studying of this technology. This is one engineer's opinion. But basically, in terms of the SQL analytics ML operations, what I hypothesize is that scan is typically going to be better on the FPGA because of this MIMD versus SIMD. There's a lot of if statements in scanning data, also decompression which typically involves bit level operations. Your SQL operations, things like join, aggregate, even project, that's going to vary depending on the regularity of the operation. The more regular it is, probably the better it's going to perform on the GPU versus the FPGA. For ML training, I think we all know this, the GPU is pretty ubiquitous and very widely used for training. And the reason for that is because that's typically is a very regular matrix operation. So things like matrix multiply, tensor product. And the other point is that they use, for training, you need to use typically floating point high precision multi-word values to do those computations. And that's amenable to the instruction set architecture that GPUs have. So that's where it's seen its benefit. Inference is an interesting one. So you would think that with training being GPU sort of specific, maybe inferences as well, which could be true, but it really depends on the precision that you're using. So there's inference algorithms, to my understanding, that are using even things like vector sets that are bits, logic 1 zeros. And in those particular cases, because of the ability to conform to bit level operations, FPGAs may have an advantage in terms of performance for inference. So, what I'm trying to get out here is, this is a taxonomy. We need to think about these kind of issues when we're accelerating, and then, back it up to our application, our understanding of our own application to make it work. So, like I said, this stuff is available today for data scientists to use. And there's two technologies I'm going to be sort of presenting some results about. One is a GPU-based acceleration technology. The other is FPGA-based. They're both available today on AWS. But I want to be clear that this is not a head-to-head comparison of performance. This is really trying to get the audience to understand the level of performance that can be gleaned from these acceleration technologies. So just to get into the experimental setup, we ran, and really from a user's perspective, right? We ran 4-node worker clusters on AWS. There's 8 vCPUs per worker, 1 executor per worker, 7 cores, leaving 1 core over for the OS. The baseline in all cases is Spark 3.0.1 run on the CPU of the worker cluster. This is, again, a benchmark suite called TPCDS. For those that aren't familiar, this is a set of business intelligence queries. They really cover the gamut of SQL operations. There's about 104 of them. We chose 90 of them for various reasons. But I want to be clear that this is the standard TPCDS queries coming right from the website, tpc.org. I won't name names, but I've seen other studies that are using modified versions of these or proprietary queries. We really want to do it from user perspective, so we use the standard TPCDS code. And then also standard TPCDS data in CSV format. However, it's gzipped, which is usually the way people store compressed data. And the other thing is that the data is all coming from the identical AWS S3 bucket. So again, this is not a head-to-head comparison because of the differences in terms of the run environment, and we'll get into that. So the name of the GPU technology, it's called Rapids. It's provided by NVIDIA. And you can allocate a Rapids cluster via AWS EMR, Elastic MapReduce, which is the managed Hadoop service. And so the cluster is comprised of G4DN.2X large, which is a standard GPU instance, has a single GPU in it. You can see the characteristics of it in terms of cores and memory. And what we did is we basically optimized the Spark configurations as recommended by the NVIDIA literature for Rapids. We did a similar thing with the Bigstream FPGA-based Spark acceleration. Now, F1 instances, which are the FPGA instances in AWS, are not yet available in EMR. We're actually working on that with AWS. But we're able to allocate them using a Bigstream provided script in much the same way. It works almost the same as EMR in terms of ease of use. And you can see the characteristics of the F1 instance. So obviously it's got a slower CPU, more memory. We have optimized Spark configuration. But I just want to emphasize that we're running on 2 different instance types. So there, there's no real comparison direct comparison to be made between the two technologies, but we do get a sampling of the performance that's possible. So this is a graph showing speedups, again, comparing running Spark 301 on the CPU versus including the GPU via the Rapids interface. And you can see that you do get speed up on an average of about 1.9x. I won't speak to the details of how Rapids works, but I can say that we use the standard TPCDS code. There was zero code change involved. And you see a spectrum of performance with the Rapid solution. So we ran the exact same experiment, but on F1 FPGA nodes for Bigstream. You see sort of a higher level of speed up. Again, not a head-to-head comparison, but this is sort of the flavor of the acceleration that you can see with this solution. Again, I can speak to this because I know that there's a spectrum of operators that we have implemented on the FPGA for acceleration. So you see a spectrum of performance levels for the different queries. So some queries are making more use of the accelerated operators than others are. And that's why you see this spectrum. But the basic overall average speed up you get over standard Spark is around 3.5, 3.66x. And by the way, I want to add that there's no slowdown with any of the queries. With Bigstream, what you get is default Spark behavior if something is not able to be accelerated. So I just want to bring out sort of how is all this possible? How can we accelerate with zero code change on this complex hardware? How can data scientists access this? And this is the way the Bigstream solution works. And the basic idea is that it's, again, a software middleware that automates the process of acceleration of Spark, okay? And the way it does that, really briefly, is that it leverages the Spark physical plan, which we call a data flow. So basically, we're able to intercept that data flow. And that data flow contains all the information about the application being run in Spark, right? We know that it's got the schema, concurrency information, operator information, the whole shebang. So if we intercept that data flow, we're able to generate accelerated code for this kind of hardware. So that includes CPUs, right? We saw the software-based acceleration. That's just in native C++. FPGAs, where we saw those results. There's another platform called Smart SSD, which is a computational storage, meaning there's an FPGA attached or directly on the storage platform. We're working with Samsung on that product, and we're taking that to market as we speak. And then, you know, roadmap is also GPU. So really, the software is a framework for automating that acceleration process onto this hardware. So the key thing is that you can get, as you've seen, we've seen up to as high as 10x acceleration end to end. But I think equally as important, and equally important for us data engineers and data scientists, is the stuff in the upper right, which is zero code changes, right? We don't want to disrupt our work processes to do this acceleration. And really, that's what these hardware acceleration approaches do provide us. So in summary, you know, hardware acceleration is here. We believe it's taking off, and especially for Spark for analytics. It's available today. It's on the cloud. It's also on premise, and it also offers zero code change, so no disruption to your work processes. And the way you want to think about it is it provides a next level of performance, but it really enhances the traditional Spark optimizations we talked about. So any optimizations you do, any optimization Spark does, Catalyst does, the optimizer, acceleration will just ride that because it's accelerating on a per task basis in general. And so the use cases for this performance, I think I don't have to go into much detail here, is basically, you know, some folks want the highest performing analytics, right? They have their infrastructure, they want the highest performing analytics on it. The ability we already mentioned to leverage more data. You know, when I was a data scientist, I used to worry about how much look back I have on my historical analytics. You know, this can really help with that. You can ingest more data sources, larger size data sources. So it really can open up the diaspora of data that you can use. And it's really overcoming cluster scaling limitations. This can be used in conjunction with cluster scaling to really give you the maximum performance for the buck. because it has these cost and power advantages over simply buying servers or expanding your AWS cloud size in the CPU realm. And so that can result in total cost of operation savings in many, many cases. So thank you. That's my talk, and I appreciate your attention. And if you have any questions or want to have further discussion, I know we have question and answer. Please feel free to contact me out of band on my email or via LinkedIn, and I'm happy to talk about this technology, which I'm very, very excited about. Thank you.